A bond is an investment. First of all, talk about bonds here. Maybe you've heard of bonds before. There are corporate bonds, there are government bonds. There are things that are really bonds that aren't called bonds, like treasury bills. Heard of treasury bills before? Federal government. You know, when they increase the national debt, that's one way they increase the national debt, if they sell treasury bills and so forth. They're selling their bonds to investors, and then they owe money to the investors, and that's part of the national debt. It's not the only thing. That's national debt. What's it up to now? 25 trillion or something? Yeah, they got to pay it back. Corporate bonds, corporations can issue bonds. It's a way to raise money. What they're doing is they're selling investments to investors. They're saying, if you give me money right now, I will pay you back over time, and you'll get some interest on your investment. Bonds are typically sold at a certain price. The price can fluctuate. Bonds have a face value that doesn't typically fluctuate. I mean, you can offer different bonds of different face values. A common amount for a face value is $1,000. Now, $1,000 bond, when you purchase that $1,000 bond, you're not going to pay $1,000. Ideally, you're paying less than 1,000, maybe 950. So you get a return on your investment in terms of this face value. But actually, sometimes you pay more than the face value. Why would you pay more than you're going to get back? Well, you don't. You still get back more than what you pay in. Otherwise, you wouldn't do it. It's got a certain face value, often $1,000, and it's something called a coupon rate. Now, this has nothing to do with coupons that you use for buying things. We have a conflict in our marriage, my wife and I. I say coupon, she says coupon. I've never been able to change her. It's okay. I love her. Anyway, okay. Coupon rate. R, like maybe 5% or something. The income stream then consists of coupons, N of them. I wish this was italics. Let's change it to italics. N coupons of amounts F times R at times 1 through N, and a final redemption value F that is the same as the face value. Actually, it doesn't always have to be the same as the face value, but it usually is. So what's going on here? It's good to draw a picture, a timeline. Make a real number line. Mark off the present, which is time 0, time 1, time 2, time 3, time 4, etc. The last time to be considering is time N. What are the units for time? Could be years. Actually, most commonly for bonds, it's half years, most commonly. So 1 would be half a year, 2 would be a full year, 3 would be 1.5 years, 4 would be 2 years, N would be N over 2 years typically. That's the most common thing, is they're called semi-annual bonds. You pay P at time 0. You get F at the end, the face value, but you get more than F at the end. You get the coupons in between of amounts F times R. FR at time 1, FR at time 2, FR at time 3, FR at time 4, etc. FR at time N minus 1, FR at time N, and also F itself, that face value at the end. Now realize again, R is going to be an interest rate. You know, you could pretend it's 5%. Though when you use these formulas, you would convert that to a decimal 0.05. So F times R is going to be smaller than F. These coupons that you get are smaller than F itself. So you get relatively small payments, N of them, at times 1 through N, and then a bigger payment also of the face value at time N. In the reverse situation, if you were taking out a loan, maybe to buy a car, that's not typically done this way, but you could pay back the loan by paying a bunch of small payments, maybe every month for 5 years. And then at the end, the loan company also says, hey, pay one big last payment. That's not the way it's typically done, but it could be done that way. This is kind of like that. I is the periodic interest rate for this investment, also known as the periodic yield rate. And that's actually the term I'm going to use more often here. Yield rate. If time is measured in years, it would be an annual rate. If time is measured in half years, as is most common, it would be a semi-annual rate, 1% per half year. Although sometimes that's quoted as an equivalent rate for a year. It's kind of confusing. Most commonly, in fact, that happens. The quote would be an equivalent full year interest rate, but to figure out the coupons, you got to use the corresponding semi-annual interest rate. Periodic here means same measurement units for time. If time is measured in years, this would be an annual yield rate. If time is measured in half years, this would be a semi-annual yield rate. You want to figure out, what is that yield rate? What kind of return on my investment am I getting? To figure it out, you have to take all these payments that you get, these coupons plus the final redemption value, and figure out what's called their present values. That's the definition of how to interpret this. But how do you actually figure out the present values in terms of I? The first payment at time 1, you need to imagine kind of finding an equivalent amount at time 0. And you do that not by dividing by I, but dividing by 1 plus I. FR over 1 plus I is the equivalent value. It's called the present value of this future payment. Present value right now at time 0 of a future payment, 1 year in the future, or one period in the future. And this essentially defines what I is. If I is 0.05, then you're dividing by 1.05, giving you a smaller number. $1 1 year from now is worth less right now. Did you know that? And that's not even considering things like investments. $1 today is worth more than $1 in the future. Again, not even considering investments, not even considering inflation. Why? Because you'd prefer to have $1 right now because you really want to go buy a candy bar. Although what are candy bars now? $2? You'd prefer to have $2 right now because you really want a candy bar. You don't want to wait a year. So it's worth more to you now. Even not considering inflation, even not considering investments. Yes, you can take those $2 and invest them. And yes, that $2 candy bar in a year might be $2.25. But even without those considerations, people prefer having their money right now. So if if $1 today is worth more than $1 in the future, that means $1 in the future is worth less today, like 95 cents or something. So to get from here to here, you got to divide by a number bigger than 1. And you got to do that kind of thing for all these payments. The second payment, though, has to go back in time 2 years. Keep saying years, 2 periods. So you got to divide by 1 plus I twice, meaning you got to divide by 1 plus I quantity squared. The third payment has to go back in time 3 periods. Now I'm running out of colors. I'm running out of patience, etc. These last 2 payments at time n have to come back in time n periods. Divide by 1 plus I to the nth power. The price of the bond now at time 0 is the present value of all those payments, meaning add them all up. So you get an equation like the one you see right here. P, the price, is the sum of all those present values of those monetary amounts. The first one at time 1, the second one at time 2, the third one at time 3, etc. through time n. And at time n, you have the coupon FR and also the face value F. The periodic yield rate is the value of I that makes this equation true, whatever the price happens to be. Actually, there's 2 ways to think about it. You could either think of this as a function of I that determines the price if you know the yield rate. More commonly, though, you think the price is known and you got to use it to figure out the yield rate. You got to solve the yield rate more commonly. Prices are often quoted on the open market without necessarily telling you yield rates. I mean, they will figure out the yield rate too, and often will tell you what that is. But the price is the thing that's determined by the market, and the yield rate comes from that. You know P, you got to solve for I. Oh my, all those I's are in denominators. That's not a polynomial in I. It's a big, crazy rational function of I. It'd be nice to have a polynomial instead. Well, that's easy to do. Let V equal 1 plus I to the negative 1, and you get a polynomial in V. Does V have a name? It does. It's called the periodic discount factor. Instead of dividing by powers of 1 plus I, you're multiplying by powers of V. And you now have a polynomial in V that you can solve for V. And once you know V, you can figure out I. Right? If V is 1 over 1 plus I, in other words, 1 plus I to the negative 1 power, you can solve that for I, multiply both sides by 1 plus I and divide both sides by V, you'll get that. Subtract 1 from both sides, I is going to be 1 over V minus 1, or with the common denominator of V, that's the same as 1 minus V over V. So once you know V, you can figure out I. Most typically, I is a small positive number, and V is a positive number slightly less than 1. For example, if I is 0.05, so that 1 plus I is 1.05, then V is 0.95238. On the other hand, if V is 0.95, and I use this formula, I'll get an I that's slightly positive. 0.0526, 5.26%. You can either think about dividing by numbers bigger than 1 to get smaller numbers, or you can think about multiplying these numbers by numbers slightly less than 1 to get smaller numbers. But this is a polynomial in V, an nth degree polynomial in general, by the fundamental theorem of algebra, is going to have n roots, some of which could be complex numbers, some of which could be negative numbers, some of which could be repeated. Which one do you pick? You kind of punt and just pick the one that makes the most financial sense. For most applications, I is slightly positive and V is slightly less than 1 and positive. Pick the one that makes the most financial sense. That's what you do. Let's do a quick example with numbers. If F is $1,000 and R is 5%, which you can convert to 0.05, and N, let's keep it relatively small, is 4, say. These two things imply F times R is $50. So visually, you're paying a certain price now for 4 payments of $50 at times 1, 2, 3, and 4, plus a final face value of 1,000 at time 4. And you're trying to figure out the yield rate. If you know the price. Now, I haven't said the price. Let's pretend we know the price. Let's say it's what you would most typically hope is true. It's less than the face value, maybe 950. Then your equation of value would be 950. In terms of V, it would be 50V plus 50V squared plus 50V cubed. These are plus signs. Plus 1,050V to the 4th. The 50V is the present value now times 0 of the first payment at time 1. Since V is, we're hoping, going to be slightly less than 1, 50V is slightly less than 50. You actually do get $50 at time 1, but its present value is smaller. 50V squared is the present value of the $50 payment at time 2. 50V cubed is the present value of the $50 payment at time 3. 1,050V to the 4th is the present value of the $1,050 payment at time 4. V is slightly less than 1. This is slightly less than 50. So is that. So is that. This is slightly less than 1,050. Though because you're doing higher and higher powers of V, the things you multiply by are getting, in fact, smaller and smaller. V squared smaller than V. V cubed smaller than V squared. V to the 4th is even smaller, right? If I use this example here, when V was 0.95, if I square that, I get 0.9025. 0.95 cubed is even smaller. 0.95 to the 4th is even smaller. Is V 0.95 here? No, I'm sure it's not. I got to solve for it. Might it be close to 0.95? I could suppose it's not too far away. You could graph this function of V on your calculator and also graph a horizontal line at 950 to solve for V. Let's solve this with Mathematica. It'll be a little quicker. Okay, probably the best thing to use is find root. Find root 900. Don't forget that's double equal signs when you're solving equations in Mathematica. 50V plus 50V squared plus 50V cubed. Yes, thank you, 950. Plus 1,050V to the 4th. Remember, though, that find root needs an initial guess. Why don't we guess something close to 0.95? 0.939336. So the periodic discount factor is what this is called, V. It's 0.939336. What does that mean I is going to be close to? It should be close to 1 minus this. It should be close to 6%. It's not going to be exactly that. The formula for I, as we saw, was 1 minus V over V. 1 minus 0.939336 over 0.939336. This should be somewhat close to 6%, 0.06. Yeah, 0.0646, 6.46%. You also could figure it out, this formula too. 1 over V minus 1. Two formulas. They're the same, right? Get a common denominator to get from here to here. So I is about 6.46%. What did I say? 6.46? Is that the only root of this polynomial? Like I said 5 minutes ago, no, it's not. What would happen if we used solve instead of find root? You don't need an initial guess, but we are solving for V, so the syntax would look like this. Two of them are evidently complex numbers, or in fact, they're even close to purely imaginary because these are effectively 0. There's our 0.939. That was our answer for V. Then find the corresponding I. Look, there's a negative answer for V. Doesn't make financial sense, though, so don't use it. If it doesn't make financial sense, we would not use it. I claim sometimes the price can actually be bigger than the face value. What if it was the price was 1,050 instead of 950? Why would you pay for such an investment? Well, you're still getting more money than you put in, because total you're getting 200 from the coupons plus 1,000. You're getting 1,200 total. So you're still getting more money than you put in. You're still getting a return on your investment. It's just going to be a smaller return. When our price was 950, we got a pretty high return. If the price is smaller than or bigger than 1,000, we're going to get a smaller return, a smaller value of I, which corresponds to a bigger value of V, actually. We'll get a V closer to 1 here. 0.96 instead of 0.93 something. The corresponding value of I will be smaller. Close to 4%, 3.6%. It's not exactly 1 minus V, right? These two are not the same thing. You do have to divide that by V to get more precisely what the yield rate is. Can I clarify anything? That's a fair amount to take in a short amount of time. This part of the video, if nothing else, might be worth watching again.